Hello and welcome to PyData Global 2025, day two. We're kicking off the general track this morning with PyData, Sparse, and Finch, presented to you by Willow and Mateusz. So if you are joining us this morning, I really encourage you to use the chat feature and engage with the speakers, engage with other attendees, drop some questions. We'll have about 5 minutes in the end for some Q&A, and would love to hear your thoughts throughout. So that's on the right side of your screen. You can share over there. But right now, I don't want to take up any more time, so I'll hand the stage over to you all.
Thanks, Tamara. Yeah, go ahead, Mateusz. Let's do the next slide. So we're here today because I think, in part, I don't know about y'all, but I'll speak for myself. I'm obsessed with array programming. Array programming is incredibly productive, and programming with these collective operations on large data sets has really changed and shaped a lot of the modern innovations in the scientific domain, in the machine learning domain. Frameworks like TensorFlow and NumPy and JAX are really shaping a lot of this innovation. These frameworks are efficient. They run at the peak processing speed on your processors, and they're easy to use. Next slide. One thing these frameworks can't really do, though, is represent things like sparsity. So we see sparsity in scientific computing with like triangular matrices or banded matrices. In social networks, we see this sort of unstructured sparsity representing connections. So here we have an adjacency matrix. And one thing to note about sparsity in particular is that if this adjacency matrix is representing the connections between triangles in this mesh, triangles only have 3 sides. And so this only has 3 non-zeros per row. It's incredibly sparse. If we were to store this using a dense representation, it would actually be infeasible. So it's really critical that we actually do represent these sparse matrices only storing the non-zeros, which adds some complexity to the implementation. In machine learning, we see more structured forms of sparsity these days, trying to improve the processing speed of the network. So we see block sparsity. And then in image processing, you can also represent things like convolution using matrix multiply if you use a special kind of sparsity where you do circular shifts of the filter. And you might even see sparsity in padded operators as well. Let's do the next slide. Sparsity is challenging. And one of the ways to think about this, right, is that in the dense world, the problems are kind of self-similar, all the way from their definition, where it's kind of a matrix vector multiply, all the way down to hardware, where it's still, small matrix vector multiplies. We have this beautiful row major relationship between where things are stored in theory and where they are represented in memory. But in the sparse world, this is really no longer the case. Because we're only storing the non-zeros, if we're only going to store the non-zero values, we kind of break this assumption. Here's an example of the CSC format, compressed sparse column. And you can see that in the val array, we're only storing the non-zeros. In the IDX array, we're only storing the locations, like which row the non-zeros reside in. And then here in this PTR array, we're storing the delineation between columns in this representation. And so the challenge comes from not just only storing the non-zeros, right? But we also need to be able to efficiently iterate over these data structures and modify our computations to only multiply the non-zeros, right? Because anything times 0 is 0. And so sparsity represents this opportunity for optimization, but we do need to modify all of our algorithms to operate on these data structures efficiently. Let's do the next slide. So this has sort of led to this situation where sparsity has fragmented support today. Support for a lot of different operations is fragmented across key libraries in the PyData ecosystem. We know that, like, in SciPy, maybe we only have 2-dimensional arrays. PyData Sparse has n-dimensional arrays. PyTorch also has some optimized n-dimensional arrays, but the support for different kinds of operations is still in progress. And then, of course, there's a desire really to have this single library central to the ecosystem that's n-dimensional, that has CPU and GPU support, that's performant, and has broad support for all of the different kinds of operations that we may actually want to use with the sparse matrix. Let's do the next slide. So this kind of leads to this situation where the implementation burden starts to grow. So we have our wish list of all of these different things we want, but because we always need to modify these operations to process the data structures, we have many different operations and many different data structures, many different algorithms that we can use to store the data structure, like a hash table or a list. And then, of course, we have these different architectures that we want to target. And this leads to a combinatorial explosion of maintenance and kernels that we need to implement. So we really believe that compilers can help. A compiler can automatically generate code for each of these situations. Let's do the next slide. So sparse tensor compilers are this emerging technology. They allow us to combine high-level descriptions of formats with high-level descriptions of kind of like the imperative version of the sparse program that we want to run. So we can sketch how we want the kernel to be implemented, and that's really helpful. The compiler can handle the rest. And so this allows us to kind of unify this ecosystem by combining all of these different definitions of sparsity, these different structures. You have like JAX, you have PyTorch, maybe you have like a NumPy algorithm, and we can compile all of these, like we can represent all of these different specifications and data structures using the same intermediate representation. So we have our tensor formats described at the top, and then we have a little bit of annotations for performance, like what kind of loop order, what kind of pointwise expression are we going to use, what kind of aggregate are we using. So if we can represent it in the unified format, then the compiler can generate efficient code for each situation. Go ahead, let's next slide. So sparse tensor compilers are very helpful for empowering performance engineers to make make efficient kernels more easily. But for the domain expert, for the user, right, they're really going to write some NumPy code. So here's our domain expert, and she's writing this NumPy code at a high level. The domain expert will also specify their array formats. Is it dense or sparse? And then the optimization part is the job for the performance engineer. So this is historically how a lot of these tensor compilers have been built. And so it was the job of the performance engineer to specify things like loop ordering, formatting, and which operations should be fused together. And then the performance engineer would put all of that into this intermediate representation that represents the optimization decisions. And then, of course, that gets compiled by this tensor compiler, and you get your results. But in order for us to really claim that the interface is this high-level productive interface that has really been battle-tested and shown to be effective, we need to automate this part of the pipeline. We can't rely on a human in the loop at this critical juncture. So instead, for this project, we have to build what we call an auto scheduler. And so the auto scheduler automatically makes a schedule, a list of the kind of optimizations that are relevant for each situation of sparsity. So this kind of technology of automatic decision making about the implementation is actually critical for this application. Slide. Yeah, so I think at this point I'll turn it over to Mateusz.
So the overall agenda here for us is to present the project overview. So what tools we're actually using here to enable the Finch compiler for the Python community. We'll see how it's actually lowered with some benchmarks, so how actually you would use it in your workflow. And then we will show you where you can find more information about it. So for the project overview, first of all, we want to introduce to you Array API standard. So the purpose is to find a common language, a common API for different libraries to use. That's something that is already supported, for example, by NumPy or JAX, where you can write the code in one way with one API and then just replace an import to use a different libraries. That's something that's already used in, for example, scikit-learn to use different backend libraries for running operations. And the tool that here we want to enable community to use is our Finch compiler that basically operates on this imperative control flow. And we want to Python community to be able to use it with the API that they're familiar with, that they use on daily basis. So some people are, for example, only familiar with SciPy Sparse. That's something that we also want to take into account when allowing people to use it. The Finch architecture in a nutshell. Here we have a few layers basically that we use for lowering. So you know the Python array API already. So that's something that you would use. And then we lower to Finch logic, where we express it in more structured way. Then the autoscheduler does all the operations, the optimizations that Willow mentioned to produce a Finch notation. And then a looplet lowering, an example that we're going to see soon, generates a Finch assembly code that then is translated to a specific backend. So either, for example, number or C code. And for our testing, there are multiple interpreters at each layer to make sure that the layer that we implemented makes sense, that it's actually implemented the way that is actually usable. A compilation example. So for this purpose, let's assume that we want to perform an element-wise multiplication. But here, to take advantage of a structure, let's assume that the second tensor is a lower triangular. So in NumPy, you know a 3L function where the upper part is zeroed. So instead of multiplying each element in both tensors, let's see how the lowering will take advantage of the fact that we only want to access the lower triangular part. So the Python API is something that you write as a user. So we define the format that is double dense layer. We pass it to the lazy. We call compute. And the Python API is then interpreted, is represented as a Finch logic. So here you can see two tables where the second one has this lower triangular mask inserted in its structure. So this is the point where you can already see where this lower triangular is present. And our element-wise operation is a map join operation with a multiplication. The Finch logic then is translated lower to Finch notation, and within Finch notation we have a notion of a declare for declaring the result tensor that we're going to return. And instead of a map join, here you can see we have a double loops. We have a nested loops for traversing the two-dimensional tensors. And each element is an increment where we read from two slots and write to the output. So at this point, it's still pretty simple. Now, moving from notation to assembly, we're going, for sake of simplicity, move already to a NumPy backend. So how the notation is translated to, let's say, NumPy assembly or NumPy code. So the two parts that we're going to focus on is lowering declare and this loop nest. We're going to do this by traversing levels of our tensors. So just to remember, these are two-dimensional dense tensors, where the second one has this lower triangular mask that's going to play an important role here. First, let's lower declare. So as the result is a two-dimensional tensor, we're going to declare it by writing a 0 to each element within the buffer. Now we would like to lower the first loop. We descend, we move to the next level. We see that each level for all the inputs and the output tensor are dense. So the loop is lowered to a lookup looplet, which then, when we lower it, results in a dense loop. So we have a for loop that starts at the NumPy extent for the first dimension. We compute some position variables that's going to be just used for accessing the right element in the buffer. Now we move to the next level because there are no other looplets to lower. And the next part, we see that we have two dense levels, but also a mask with a dense level. So that's, at this point, we see that this loop is going to be lowered a little bit differently. The loop is lowered to a looplet nest with a sequence and two lookups for head and tail, where split is a variable that's the, like, let's say a barrier here. And the sequence and lookup that we're going to lower will result in two loops. So that's the loop for head and tail, where we start, where we finish, and we start at I0 variable. Now we have the leaf looplets that we are also lowering right now, which results in accesses to the result tensor. So again, some position variables. Additionally, we have a check where we assert that this is the first time we access the result tensor. And the last element to lower are accesses to the input tensors. And here, it's just access to the buffers. But the only thing different here is in the second loop, where the A1 is, instead of accessing it, we just write 0, because that's where we know that the upper triangular is. So that's where all the zeros are by the structure of the input tensor that we received. So we finished lowering all looplets. Now let's think about some simplifications that we can apply here. For example, we know that 0 is an annihilator for a multiplication, so that part can be automatically removed and replaced with 0. Another thing to notice here in simplification is that we assert that the value is 0, because that's the first time we access the buffer, and you write immediately 0. So the whole contents of a second loop can be also removed. And the last simplification here, if we see that there is a loop with an empty body, we can remove that loop. And at this point, we completed the lowering, and that's a kernel that is ready to use with NumPy backend that takes advantage of the structure of inputs, where our operation will only traverse the elements of the lower triangular. So we've seen how this machinery works, how actually we can compile our kernels with our inputs. Let's see some use cases and some performance gains that we managed to achieve here. So the workflow that you as a user will be exposed to is that you have some numerical code written, which might be similar, for example, to NumPy. Then you want to make sure that it's Array API compatible. So you rewrite it in a way that every function, every mechanism there is present in the array API. And the second step in this workflow is sparsifying it. So you can move a certain parts of your code to a separate function, write Finch compile to JIT compile that part, make sure that you wrap your inputs in some tensors with some format. So that's the workflow that we're going to show you in a HITS algorithm. So that's an algorithm taken from Graph plus Algorithms repository, which is used in network analysis. So it's a very short one. There are some Graph plus custom APIs. So for example, left shift for assignments. We have some vector classes. So that's only for Graph plus purpose. Then we want to make sure that it's array API compatible. So let's say we rewrite it so we can then run it with NumPy, with JAX, anything that supports array API. Then we would like to, for the sparsification, we would like to JIT compile the part that is present in a loop, in a power iteration part. And we do this by moving it to a separate function. We write the Sparse compile decorator and call that function in an appropriate place. So then when we call our HITS algorithm, this part gets compiled and we just execute again the kernel. And this workflow that I just showed you in this example is something that we applied to TensorTools library. So that's a library written for NumPy. And it uses canonical polyadic decomposition algorithm in research in tensor component analysis. We decided to take a function that has a masked version of it, make it array API compatible, which wasn't really that much to change, and sparsify the part that it's in a loop, or the part that takes most of the computations. For the results, for some low density of 3%, we got a speed up, over 7 times speed up on our infrastructure. So we don't provide code here, but in my fork, there is a PR where you actually can see how much code changed there to make it array API compatible and to make it JIT compile with our Finch. So the code change was rather small. It wasn't just rewriting the whole function. It was a few small changes, and then you just get the speed up for running your CP decomposition. So I can paste a link later in the chat. You can try yourself what we just showed you. So it's available as a Finch tensor library on PyPI. This uses Julia call for bringing Julia implementation in place. We also have the pure Python rewrite that we're going to show you in a landscape in a minute. Oh, actually, it's that slide. So here you can see here you can go to finch-tensor.org. This is the landing page of our ecosystem. And apart from the pure Julia implementation that you can use, we have the Python wrapper, which we benchmarked and show our use cases. And the ongoing work is a rewrite to pure Python, the whole compiler, so that you can use it without Julia runtime, but with for example, NumPy as a backend for kernel generation. Last but not least, we have some other topics in overall ecosystem integration for sparsity. One of them is bin sparse file format for standardized interchange format. The backend that we showed you, the solution is also available within PyData sparse library. So that's an n-dimensional sparse library for with NumPy as a backend for Python, and we want to provide the Finch as one of the backends that you can select with environment variable. Last thing that we want to talk a little bit is the bin sparse storage format. So that's the format that also we push to introduce to the community to unify, to standardize the array computations in Python even more. So the idea is to support multiple formats here, and also in a cross-platform way. So this can be used efficiently by the users. So that's something that you also can read about in our landing page and in our resources. So that was all that we presented for today. Thank you so much for listening. Again, feel free to visit our page to learn more about it. And again, the 2026 is the year when we want to push for Finch Lite to make it available in some first stage to the community. Thank you very much.
Thank you both so much for the wonderful presentation. Let's see, if anybody has any questions, go ahead and drop those now. It looks like we had this one, and Willow's already answered that you'll be sharing the slides.
But Mateusz can also step back and show the before after as well. I'll upload like a link to like a PDF or something.
Here is what they said. I'm just trying to understand the lowering more. I thought it was very interesting. So
yeah, and we have academic papers that describe this lowering process as well. It was developed to be flexible to a wide variety of matrix structures like triangular matrices or run length encoded matrices or sparse matrices. Hopefully, using a really extensible lowering process can make it so the library is a little bit future-proofed and able to extend to new applications.
awesome. Well,
And I have the link here in the chat for the slides. But you can also check out finchtensor.org and follow the links to some publications.
Awesome. And you all can drop those in the resources as well, and then everybody can go back and reference that. But it doesn't look like we have any other questions. Thank you both so much for your time and dedication to PyData Global. Thank you, everybody, for being here. And we'll see you in a session later today. Thank you.
Thank you.